So welcome everybody to the first public lecture of our Machine Learning and Economics Summer Institute. We will kick off the Summer Institute with an introductory lecture by Sendhil Mullainathan. Sendhil, the floor is yours.
Thanks everyone. Let me just share my screen and I will get going. Okay, it's great to have everyone here joining us, both people in summer school and then people joining us on the live stream. I basically want to just dive in. The goal of my lecture is to contextualize at a very high level. Jann is going to dive into a lot of the econometric details. So my goal is to simply just answer a set of questions that are very, very high level. And to pose the questions, let me just start by making an observation. Machine learning is very familiar to anyone who's done empirical work in economics because it's basically an empirical tool. And since we have people of very diverse backgrounds, let me just walk you through exactly why that is. So you take a canonical task like face detection, and here's the bounding box for the face. And the question in the face detection task is, if I gave you a little box, is there a face in the box? Now, there's something in the middle, a connet, whatever you want. But ultimately, what it outputs is a binary variable. Is this a face or not? So when you say that machine learning is familiar in being an empirical tool, it's extremely familiar. It's a relationship between an x. In this case, the x is, k by k array, but basically just a long vector. And in each element of the vector is something about color or intensity. And that's the x. It's just a set of binary variables or C area variables. And the output is a y. And it's even very, very familiar in that what are you doing? You're doing loss minimization. You're looking for an algorithm that makes a prediction about what the y is going to be, and you're trying to minimize some expected loss. Like, this is the beginning of any econometrics textbook. So it's not just familiar, it's incredibly familiar. And since we know how to use empirical tools, great. We're just going to go ahead and use it. I'm laying this out in this type of clarity because I think this way of thinking about machine learning is very seductive, is the way I think most people, without ever articulating it, think about it. But it's also very dangerous, and it's what leads to a lot of bad applications. And so what I want to now do is to ask, if you approach the world with this way, well, what would you do and what goes wrong? Well, the first thing you would do is you would say, holy cow, I know what this is. This is arbitrage. There's something over here that does something, and it's not used in my field, and I'm just going to go and sell it. For those of you who don't know Spanish, I mean, whatever, you can figure this out yourself. And so you might say this is economics, and the arbitrage is machine learning. And one of my students said I should have done this instead, but that just seemed to me a bit overkill. So that arbitrage approach is just take this hammer, go look for some nails, and there you are, you're all done. If you follow that approach, the thing you would do is you might pick up the elements of statistical learning and say, great, I'm just going to learn from this book. But there you'd encounter problem number one. The first thing you'd encounter is things that you are like, wait, this is machine learning? Like linear methods for regression? I think I know what that is. I know what a kernel smoother is. The other thing that you'd encounter is not that there are familiar things already on this list, but what's missing, actually, I don't know how I created this hole here, but anyway, so what's missing is, okay, I do it, but I'm in the business of hypothesis testing. How do I get a valid confidence interval? How do I get a valid test? What is all of this? So the existing material, if you approach it with this arbitrage approach, has both weird overlap that you don't know what to make of and some big holes. So it doesn't precisely illustrate what's new here. And it's not an econometric framework. You don't know what's guaranteed and what's not. Until you really try to absorb statistical tools like this, I think for many people, they don't appreciate how much the backbone of econometrics that you're taught gives you tons of additional tools that you're not really, you kind of learn it, you aren't really fully aware of. So as an example, you could run lasso, but when does lasso give you unbiased coefficients? Does it ever? When does you say, oh, look, lasso picked out these 5 variables? What are the odds it picked them out at random? What are the odds that when it picks them out, that conditionally those are the true variables? Do you have an odds, like how would you do a statistical test on that? Did it pick the true variable? And if there are some theorems that claim it, what assumptions are being made in those theorems? Do I buy those assumptions? For example, there are plenty of theorems that tell you that linear regression gives you causally meaningful coefficients. But you might not believe those theorems if you believe they're omitted variables. So what is needed to make these identifying assumptions, and do you believe those things? So this is an example of the kind of things that's really quite missing, and it makes it very hard to apply these tools to a social science or hypothesis testing framework. And one reason you should be very wary is remember what these tools are built for. And I want to pause here because this is probably the biggest difference between these fields that has really blown up in the last 5 years. We use statistics because we need hypothesis testing. Machine learning was not built using statistics for hypothesis testing. Statistics was a convenient thing off the shelf to solve an engineering problem. There is no hypothesis test to be done in face recognition. There is simply an engineering problem. So we're taking tools that are meant for engineering purposes because they share the common language of statistics and trying to repurpose them. And that's going to be the easy danger that arises. So what's needed? What we need to integrate this material into econometrics. So we'll do some of that today. And we'll answer the question, how does it do well? Where does it do badly? We need to place it in the standard toolbox. And we'll do that a bunch of the lectures today and tomorrow, integrate it with causal inference, integrate it with other things. And there's a lot of interesting econometrics you'll learn. And we need to understand where it can be used. So if I go back to the arbitrage argument, understand what makes a good arbitrage, what makes a bad arbitrage. What is a good application of machine learning in economics, in public policy? And that's what we'll do sort of starting end of Tuesday to Friday. So these are the 3 things. I wanted to give an overview of these 3 elements today, and then I'll hand it over to Jann. So let's start with integrating this material into econometrics. A lot of this, almost all of everything I'll talk about today, in fact, basically everything, is from this paper with Jann in the Journal of Economic Perspectives. So if I go too fast, or if you want some references, this is not a bad place to start. Okay, so let's start with an example of what machine learning can look like in practice, because that'll help us understand how we place it in the standard toolbox. So for this, I have like a little toy problem. The American Housing Survey is basically a large survey of houses where we know their characteristics and we know the price. And it raises a very simple problem that you could do, which is Y, like the face, is the house price. X is the characteristics. So we go ahead and predict house prices. Okay. Now, one way you could predict house prices is you could run, there are only 142 variables, you could run a linear regression. And you find that that does pretty well. It has an R squared and the holdout of about 41.7%. Another way you could do it is you could apply some simple machine learning tools. An example is a decision tree. Decision trees are just another functional form. Instead of simply running a linear regression, you take one of the variables, are there less than 6.5 rooms, and you split the data, and then you make a prediction. That's a tree of depth 1. You could have a tree of depth 2. Now, I split this way, and I'm splitting what region is a house in. I split this way, and I split whether it's square footage is big. And you can continue this way and build a very, very, very deep tree. So all of these different algorithms you encounter, they're really just nothing more than functional forms. In fact, they are literally just different functional forms on the problem. It's kind of an obvious point to make, but you should just keep that in mind, because there's a conflation here, because we talk a lot about, oh, there's a new algorithm. It's just a different functional form you've imposed on what you're looking for. And here we've estimated that for a bunch of different functional forms, including one functional form, which is the mishmash of all the other functional forms, which is an ensemble. And one thing you notice is that the ensemble does a little bit better in R squared, about 45.9% versus 41.7%. And its improvements are largely in the middle of the distribution. So one observation I make here is that the predictive gain in these social science applications is not always huge. It can be big and it can make a sizable difference, but it is not always of the type face detection went from being an undoable task to being almost an AUC of 1. And that's the thing to think about. And that's because our tasks have a lot of intrinsic noise. So there's just a ton, and Annie Liang will talk about, there's just a ton of unpredictability. So modest looking gains in R squared space can be pretty big. All right. The key features of all these models that I just showed you is that they're novel functional forms. But the second key feature, and to me, this is the differentiator between machine learning and most of the tools that you've learned so far, is they're effectively high dimensional. What I mean by that is, think of the decision tree. It can keep going and going. It can go so far down so that you have more nodes than you have data points. Effectively, you can allow for, even though here we only have 142 variables, by allowing for interactions, which is what the decision tree does, it's what gradient boosted tree, it's what all these models do. They allow for different functional forms. Effectively, you have an almost infinite amount of, not infinite, but very large relative sample amount of variables that are entering the regression. So machine learning is like estimation, like you've done off the bat all the way, but it is high dimensional estimation. In a way that people often think about this, lasso is the easiest one, is the case where there are a lot more variables than there are data points. So think of the matrix as being wide rather than long. In a lot of social science applications, there just aren't that many variables. So actually having width involves using interaction terms to create width. But in effect, you end up with the same high dimensionality. All right. I want to point out there is a small literature starting out now called the illusion of sparsity, which is worth talking about. One way you can think about machine learning is you've got all these variables on the right and you're picking the few that matter, which is the sparsity case. A different way you can think about it is that the function you're going to end up with is enormously complicated. And I think when you think about lasso in a naive way, it makes you think, oh, machine learning is picking out simple models. Quite the opposite. Machine learning is helping you handle very complex functional forms. And so that's something that as you just kind of pay attention as things happen, you'll see it's not about picking off a few variables out of 10,000 that matter. Okay, so let's go back to this example. We've got things like convnets, which you've probably all heard of. In these examples, because when we build a convolutional net, we're building all of these layers, the effective number of variables can end up in the hundreds of millions, even when your data points are in the thousands, 10,000s, the number of parameters that are being estimated. So one thing that's very easy to do is just to do a counting exercise of how many parameters are we estimating. So this is all a buildup to just get to the point of saying, machine learning is familiar in being an empirical tool, but it's unfamiliar in allowing for high dimensional inputs. And that's where the road sort of forks. All right. You can call this applied high dimensional non-parametrics if that's what you want, but that's effectively what this whole activity is. So let's place this in the standard toolbox. If I were to do it, it would look something like this. The traditional approach is fit y with x, and that's low dimensional. Machine learning is fit y with x, and it's high dimensional. There you go. It's just better. And this is what I was alluding to earlier. If you have this way of thinking, right now, from this slide, what's the trade-off? There's no trade-off. What should you use? You should always just use a machine learning estimator. There's nothing lost. I mean, why would you run linear regression? Always run lasso. Why would you run, I mean, always put in everything you can. So the thing you should sort of think about and focus on a little bit is to ask yourself, how do I think of this trade-off? What is the crux of what am I giving? What am I giving up to get high dimensionality? And if you can't answer the question, something is wrong. And that's what I'm going to try and help you answer here. And Jann is going to go into greater detail. Because if you can't answer it, it feels just like a magic bullet. Oh, it can just handle high dimensionality. And of course it can't. Something must give. You know something must give, because if the rank condition is violated, something goes wrong. So how can this thing work? To see what something must give, let's go back to the face detection task. Remember, this is an engineering activity. In that task, what's the price we pay? Well, to see the price we pay, notice what the goal of face detection was. The goal of face detection was, is there a face? Predict whether there's a face. How does that differ from what we normally try to do? Well, in prediction, pick a function that predicts y. We're trying to do things like, does this image contain a face? What is the price of this house? But whenever you run, like, say, a simple regression, what's the first thing you do? You look at the coefficients. Your goal was not to find a function that predicts y. I mean, sure, that's what you did. That's the loss minimization. Your goal was estimation. Your goal was to make inferences about the parameters f that relates y and x. Now, this would be a little awkward in the face thing. It would be, does this pixel combination affect whether this still looks like a face holding all other pixels constant? You do that a little bit with some of when you're trying to do explainability or interpretability of a model, but it wasn't the core goal. Your core goal was not this coefficient. Similarly, in the house price case, we might be interested in, does adding a bathroom increase house price? That's a different activity than what will be the price of this house. So the goal of prediction is loss minimization. Find a set of coefficients that minimize loss, out of sample loss. So use the data that does well. The goal of parameter estimation is consistency. Very often, you're looking to find an estimated set of parameters that go towards a true model. Notice how different these are. In the first case, loss minimization is the goal. In the second case, when we're trying to get consistent parameters, yes, we minimize losses, but we minimize losses to accomplish the goal of getting consistent parameter estimates. So I want you to see how different these goals are. I think many people haven't really understood what goes on in a two-variable regression and how different prediction is from estimation. So I'll start with the simplest example. We've got two variables, x and w, okay? Suppose you have an estimation problem. You run the regression, you get this estimate, all right? You then get coefficients. These are, and it's got standard errors. Unfortunately, nothing is significant. And so that's what you get. So neither of your beta x nor beta w are significant. So now let's ask, what would I do if this were different as a prediction problem? I mean, I'd still run the regression. And let's suppose I'm restricted to linear predictors. So the best I could probably do is this beta x, beta w. Put aside shrinkage and things like that. Just at some core level, what structurally changes about the problem? Well, what structurally changes about the problem is you see standard errors and say, oh, there may be no predictive value signal in x and w for y, right? Because beta x is noisy, beta w is noisy. So from this, you say, well, I mean, maybe there's signal because it's true. There's, these confidence intervals aren't that big. Maybe it's working out. No, in fact, I want to tell you something. Just pause for a minute and think about the following. It's possible to have arbitrarily large amounts of signal, R squareds, predictive power of 1 for y from this graph. Just think about how that's possible. Beta is noisy, beta x is noisy, beta w is noisy, but holding that constant, there could be arbitrarily large power here for predicting y. And if you can understand why that is the case, then you'll see why prediction is so different from estimation. Just take a minute and think about it. All right, I'm going to show you now what I think would be it. When you look at this, you imagine the confidence interval looks like this, the joint confidence interval. Why should it look like that? If x and w covary strongly, it could look like this. If it looks like this, you have arbitrarily large predictive power. either X or W is very predictive of Y, but you just don't know which one. So the big confidence intervals in X and the big confidence interval in W are telling you, I can't tell you that X is significant. I can't tell you that W is significant. But the joint confidence interval is telling you, oh, X and W together are very significant. And that's the difference between prediction and estimation. In estimation, we have to make inferences about individual coefficients. In prediction, we just have to make inferences about the joint predictive power of all of these variables. And it's much easier to make those inferences. Okay. So what's the consequence of this? Well, the consequence of what I've just told you is that prediction works well because it doesn't try to adjudicate between predictors that have similar predictive power. Take the house price example. If I don't have to decide whether it's exactly number of rooms, number of bathrooms, square footage, if I don't have to decide exactly which of these covariating variables is doing the work, I can hoover together a lot of predictive power. Prediction does not need to decide which variable is the active ingredient. It simply just needs to know that the collage together provides signal. So let's go back to this example and see what this implies. What this implies is, take the lasso predictor here. I just want to show you something that can happen there. So here we've graphed which variables the lasso predictor picks. And we've put the zeros in white and the non-zeros in black. And of all the variables we gave the algorithm, you can see which ones are picked. Now this is done in a random slice of the data. If you thought this was a good estimator, and you thought that, put aside a little bit the confidence intervals, assume that basically everything that Lasso picked are the true variables. If I were to do this exercise again on another random slice of the data, the strip should look about the same. There'll be some bop due to noise. In fact, if you do it again, it looks nothing like each other. Here are 10 different draws, 10 different repetitions of this. And Lasso is picking different variables basically every time. A few variables persist. But if you were to look at any one of these draws and be like, oh, look how important these variables are. Well, guess what? In many of your draws, you never even would have shown up. Is this a problem? No, it's a prediction algorithm. What we just saw is it tells you that together these variables are powerful. Across all these draws, Lasso is equally predictive. It stays equally predictive. But because these variables covary, it has different ways of assembling them. Jann will explain, I think, in his talk, why this is not just some sort of bug. This is the intrinsic reason you're able to do high-dimensional prediction, is because you're willing to give up on adjudicating between covariances. And there is simply no way around that activity. And so if you want to understand machine learning versus traditional estimation that you're used to, you used to have make strict assumptions about the data generating process, whereas now you're able to allow for very flexible functional forms. But what you give up is you give up parameter inferences, whereas now you're only able to make predictive inferences. To put this in a very trivial way, in a y on x times beta type setup, traditional estimators give you a lot of power for estimating beta hat. Machine learning gives you a lot of power for estimating y hat. Don't confuse a beta hat problem for a y hat problem, and don't confuse a y hat problem for a beta hat problem. And understanding there are two very different problems is where I would put this into the econometric framework. So where can this be used? So once I've laid it out like this, well, it's obvious, it's find y hat problems. To which you'll probably tell me, that's great for engineering tasks, but for what I do and for social science, there aren't really y hat problems out there. I mean, I don't make predictions. I am in the business of finding meaningful coefficients. Economics is about coefficients and causation. So what I hope to illustrate to you in the little bit of time I have left, and then in the rest of the summer school, is that in fact, prediction has great value in economics. Untapped value. It's because it's not an activity we've done before at In macro, they've done a lot of it. Here I'm talking about micro prediction. It's not an activity that's been done that much in economics, but that there is a large area for it to be used. So let me just walk you through a few places. The first place is you're already doing a lot of prediction without realizing it. In a bunch of estimators you've done, there are y-hat problems. Let me give you an example. Many of you have surely done a propensity score estimator or know what a propensity score estimator is. You're trying to find groups that are similar. You're trying to find the treatment effect. So here's treatment 1, treatment 0. You're trying to find a propensity score. So for this person who is treated, you'd like to find someone who's a good control. Okay? Without question, the object you're estimating, tau, is a beta. The treatment effect is a beta. But what is the propensity score object? So treatment effects are beta hats, but the propensity score is a y hat. You're trying to say, find a unit whose probability of being treated is as similar as mine. Probability of being treated is a P of X. It's a thing that sits outside the X. So weirdly, every propensity score estimator has built into it a y hat. Once you realize this, you'll realize every time you do a control variable setup, that's a y hat. You run y on X, the variable of interest, and you say, I'm going to control for a bunch of stuff. But you don't care about what those coefficients are. One way you can tell you don't care about what those coefficients are is you put in random effects and fixed effects. You're just trying to control for the residual. That is a hat problem of the type y hat. It's the residual of the y hat. IV, what is the first stage of IV but get the best hat you can for the variable of interest? Treatment heterogeneity. We're going to talk about this on Thursday at length, I think, and is that right, Jann? I think it's Thursday. So but treatment heterogeneity and experimental stuff, it looks like a beta hat problem because you're trying to get tau, the treatment effect. But since you're trying to get tau of X, tau hat becomes an object that looks just like y hat. So once you understand you're trying to create these y hat-like variables, you'll see that a lot of things you already do fit this mold, even things firmly within the causal framework. And a lot of what you'll see today and tomorrow fits this, this kind of activity. Okay. The second use is that y hat machine learning type problems open up new data. So I'll give you some examples. This is my favorite example of a satellite image, because I often just ask people, like, what is the island nation this is a photo of? And most people don't really know, and partly because it's a lie. It's not really an island nation. This is South Korea. This is North Korea, which this is literally, there is no nighttime lights. That is how poor North Korea is. Why is this important? If you looked at the GDP measures of North Korea that North Korea puts out, they're doing extremely well. But of course, we don't trust their GDP measures. This simple luminosity at night has proven to be a really powerful way of estimating GDP of countries at scale and real time and in very, very small pockets. Satellite images, not just at night, but during the day, have proven incredibly powerful for predicting poverty rates. So think of what this opens up to you. Imaging suddenly becomes a data set that you could use, and not just get data. And this is, you'll hear from Josh, he's used here not imaging, but cell phone data, another rich data source, to be able to predict income and poverty at each level. Another example of new data that's opened up is financial data. We tend to think of finance as being full of numbers, volume, stock trades, blah, blah, blah. But you know what it's actually full of? Language. On the right here is a 10K form. Companies file tons of 10K forms. In 2006, there were 38.8 million words that were produced by just the companies that, just in their 10K forms alone. Finance is not a quantitative field, it's a qualitative field. There's more language produced about finance than there is numbers produced about finance. And here's a really nice paper I like that used the language in the 10K forms and basically showed that language is incredibly useful. That's just using just history, and here it's using history and language, is incredibly useful for predicting future volatility of stocks. So it's just a smattering, and you'll see more new data stuff throughout. But what does the new data have to do with ML? Well, to make a use of a data set like satellite images or language data sets, you have to turn the inputs, which are merely pixels or words, into something meaningful, something that allows it to be used in usual data. So these predictors that can work with these new data sets, typically either you're using the new data and processing it, or you're going to use the new data directly into your task, as you saw in the language example in finance. So being able to use this rich new data, I think, totally transform. If you just think of any field that you're interested in and just say, I'm going to put aside the quantitative data and ask where there sits, and now you'll see tons of image, language, high-dimensional data that sit out there. Finally, it opens up totally new problems. And this is probably what I'm personally most excited about, in that these are not causal inference questions of the type that I would have asked 5 years ago. They're a different kind of question. They're predictive inference questions. And they start with the observation that many of the decisions that we rely on in the world, many of the most important decisions, are predictive in nature. And I'll explain what I mean in a second. We reflexively think policy is about causal inference, but in fact, it need not be. And let me walk you through a simple example. And in this example, it's going to be about a pretty, I guess I'd say, toy policy decision. So imagine you are head of you're agriculture minister of a country that's having a massive drought. And somebody comes to you and says, I can do a rain dance that will bring rain to this country. And you as the agricultural minister are forced to answer the question, do I want to buy this rain dance? Alternatively, suppose you're minister of a country and you're going to work that morning and you're thinking to yourself, should I take an umbrella to work? It's a different country. They have problems with rain. Those are two questions being made, two choices being made. They're clearly decisions with payoffs. So consider everything they have in common. They're decisions with payoffs. To help answer them, they both rely on data of the type. There's a Y variable, rain in both cases. There's X variable, and you're asking, I'd like to somehow relate X to Y. So both use data to estimate functions Y equals F of X. But you can see where I'm headed with this. Rain dance is a causal inference problem. Does rain dance cause rain? The umbrella is a pure prediction problem. So you can see that even though these are both decisions, one of them has a causal germ and the other has a predictive germ. So how do you make sense of that? I want to help you make sense of this a little bit by looking at a graph of what's going on. So let's look at the rain dance. There's a bunch of X's. They might influence Y. There's one particular X of interest to us, a decision, rain dance, that we wonder if it influences Y. Together, the rain influences our payoffs. That's what I'm going to call a causal inference problem. We're interested in, is this arrow there or not?
So is the question we are trying to answer one or the other? Is it early stage?
Oh. And so okay, there we go. We're interested in whether the rain dance influences rain. And experiments are useful for this. Now let's look at the umbrella problem. In the umbrella problem, it looks very similar. There's atmospheric conditions X that go to Y. There's an umbrella, a decision, but notice, whatever you may think, the umbrella, you're deciding to take the umbrella doesn't have a causal effect on rain, though it may feel like that some days. The umbrella affects payoffs. And this distinction as to whether the decision is downstream from the y variable or upstream from the y variable is the big difference between causal decisions and predictive decisions. And this is where machine learning can be useful. If it's helpful, this is the joint graph, and you're trying to make a decision with x0. Take the total derivative of the payoffs, and you get these two terms. This is prediction. The direct effect of the decision, umbrella, can depend on the y variable, rain. That's where prediction is helpful. By telling you what the y variable is, it can help you make a better decision. This is causation. Does the variable itself affect y? So this is y hat problems. This is beta hat problems. So between the graph and the derivative, you can see that in any generic decision problem, there's going to be predictive elements and causal elements. Okay. And I just want to point out, a lot of the time people will say, oh, but the world is actually causal, machine learning. In this formula, everything is causal. The question is merely, where does your decision sit? The causality we need from the estimator is the function of the unknown that we're trying to estimate. Okay, so I want to tell you this. I want to talk about how prediction opens up totally new problems. And let me give you an example. So every year in the United States, there are 12 million arrests. And right after people are arrested, there's a choice that has to be made. The choice is, should people sit in jail while waiting for trial, or should people be sent home? About 750,000 people sit in jail waiting for trial. And in fact, it's such a big effect that this is about 1/3 of the incarcerated population in the United States are people simply waiting. They're not people who've been found guilty of anything. They're just waiting for trial. And they'll wait for a long time. The average duration is 2 to 3 months of a person who's just waiting for trial. And sometimes it's as high as 9 to 12 months. This is such big numbers. That's why that a lot of time, if they are found guilty, sentences are time already served because they've been waiting for trial for so long. So what is the judge doing in pretrial? Well, they take the defendant history, you come before the judge, and the judge has to make a prediction as to whether you'll commit a crime while waiting for trial. Now, this is a little more complicated. I won't go in detail, but it's a combination of, do you pose public safety risk and flight risk? Will you show up back? Will you show up again? So what's the judge doing? Well, this is an umbrella problem. The judge is taking defendant history and forming a prediction. And that's exactly the kind of thing an algorithm could do. And what is the value add of doing an algorithm? Well, here's what we've done with a large set of data from New York. This is from a paper in 2017, 18, something like that. So the paper, we built the predictor, and we've arranged on the left what would happen if we released, according to the algorithm's predicted risk, what would the crime rate be? If we release no one, we get no crime. And the curve here maps out what happens if we release more and more people until you release everybody. So how do we decide how the algorithm is doing here? Well, let's compare it to what the judge does. The judge releases people. Oh, this is a little off. Let me, oh, yeah, sorry. This illustration is a law. The judge releases 11.3, ends up at a crime rate of 11.3% and jails 26.3% people to do it. The algorithm accomplishes the exact same crime rate with 40% fewer people in jail. In effect, the algorithm, because it ranks people's risk better, can release a lot more people. 40% fewer is a huge policy gain. Now, that's just an illustration of one example of a problem, but there are problems that arise. The first problem is, in the figure I just showed you, nobody has data on what the jailed would do if they released. So we don't have labels for everybody to train the algorithm. We have labels only on the released. This creates a selective labels problem. How should I make inferences about the released? Notice this is not an inference about the betas. This is an inference about the Ys of the released. This is especially problematic because there are unobservable factors that go into the judge's decision. So this is like a very common selection bias that you'll be familiar with. The second problem is that judge preferences can be very complicated. Are judges really trying to rank order by crime risk? What is crime risk? I mean, do they care about some crimes more than others? Maybe they have other issues going on, like they care about the equitableness of their decisions. They might care about certain groups more than others. We as society might care that certain groups are not being put in jail at higher rates than they ought to be. In fact, the bulk of the paper was not the estimation of the machine learning algorithm. It was solving these econometric challenges. And as a result, a bunch of things have to be carefully accounted for. And Jens will talk about algorithmic bias tomorrow afternoon. The result is, it's not just technology transfer. Building the actual algorithm is not the hard part. And you'll see this in a lot of the things you use to apply it. It's navigating these microeconometric issues. And yet these issues are largely ignored in machine learning. Let me pause on this and just point out, the interesting part of being in this field at this moment is to not do the mechanical applications. It's to be live to these type of complexities. These complexities, like selective labels, omitted payoffs, the thing that make it a non-natural fit to apply machine learning, are what create both econometrically interesting questions to resolve and also applied questions and work that needs to be done. And so economists have a large role to play here. And there are many more problems like this. Jens will talk a little about this tomorrow, but there are many more problems in the world where the core problem is predictive, where we're not asking what works, we're asking who and when. If you want to know, does this program work? I mean, that's an experiment. If you're asking who should get what, when should we do this, very often those are predictive problems. They require a clear goal that's represented in the data, and they require individualization. I want to pause on the clear goal. I want to point out there are many, many, many crappy applications of machine learning. So pre-trial, there was a clear goal, and there's still a bunch of issues. But take sentencing. What's the goal in sentencing? What's the label to predict? You'll see a bunch of sentencing papers that use the label as recidivism. But is the judge's goal in sentencing minimize recidivism? No, they have a ton of things they're optimizing. So understanding the problem you're applying to and asking, does it really fit a very careful predictive model is key. But when you do that, there's a bunch of things. Tomorrow, not tomorrow, I think Wednesday, Josh Blumenstock will talk to you about how we can use cell phone data to better find who's poor and target poverty. There's a bunch of problems that arise when people are unemployed, because one of the key things an unemployed person wants to know is, how long will I be unemployed? That's a pure prediction problem. There's a ton of problems in finance. A key thing that every person wants to know, say, for example, when they're buying a house, is, can I afford this house? If I buy this house, will I have high eviction rate, late payment default? Take something like teachers in education. There's a lot of work that looks at the experimental effect of an additional teacher. That's clearly a beta hat problem. But holding that constant, how do you know who makes a good teacher? That's a clear prediction problem. There's some interview and there's some prediction people are making about the performance of the teacher or the performance of the students under that teacher. Okay, let me end that bit by saying, I think the causal inference revolution focused economists on policy impact, which is great. I think what's happening now is we're starting to see many more data-driven decisions, and machine learning can change that huge part of an unexplored part of the space of predictive decisions. The last two, and then I will stop, is that economic tools can also improve machine learning. This isn't a one-way street. I've given you some examples. Selective labels and omitted payoff bias are two really good examples. Our ability to morph quasi-experimental methods and merge them with machine learning to understand predictive problems is great, but there are also very firm econometric foundations to be laid for predictive inference. When I do these predictive problems, I often find, I'm like, there's no econometrics I can even draw on to make some of the statements I want to make. And since there are more and more people doing such problems, that seems like a very important area to resolve. Another example is modeling algorithmic bias. As you've probably read, there's a ton of discussion around, oh, algorithms are biased, and what should we do about them? But that's not a computer science question. That is exactly a question that is at the heart of sort of econometrics. There's data, there's inferences from the data, there's estimators from the data, and those tend to have some disparate impact. This is what economics has been doing for a long time, and I think it can contribute to this discussion quite heavily. Finally, modeling how people respond to algorithms, which in turn leads to a distribution shift from the original training data. And these are all examples of, I think, economics can be super valuable here. So while the arbitrage, I thought, could look in one direction, increasingly, I'm sort of convinced it could actually move in the other direction. There's as much arbitrage to be done in moving economics into machine learning as there is moving machine learning into economics. Okay. Finally, I'll do this very briefly. Prediction can aid in economic theorizing. And I think there's sort of three ways this can happen. I think this is a really wonderful tool for finding novel hypotheses. Ziad will describe this on Wednesday. It also provides a tool for doing very different ways of testing theories than we're normally used to doing, and for doing science and discovery. This is probably the bit I'm most excited about, because I think the world of sort of hypothesis testing provides a tool, but I think machine learning is going to give us a very new way of working with science. So let me conclude. I think prediction is an inherently important scientific tool. It's different from causal inference, but it's highly complementary. It can help us do causal inference better. But whenever a new tool comes along, people first use it to solve old problems. But eventually the big gains do not come from the new tool solving old problems. It comes from the new tool helping us solve new problems. In fact, changing the entire scope of the discipline. This happened with causal inference, it happened with behavioral economics, and I think machine learning is going to totally change what kind of questions we even tackle. Okay, let me stop there.
Great, thank you, Sendhil. Happy to pause for a few questions before we move to the next part. Any questions or comments from you guys? Feel free to just unmute and ask, and I'm going to get ready here. Okay, so in that case, let me just continue. For this part, Ziad will handle any questions in the chat. So feel free to just ask questions in chat or just say that you have a question, and then I can pause at certain points to take those questions. In general, I really encourage you guys to ask as many questions as you can to make sure that this is helpful. Right, so I want to take one part of Sendhil's talk, which is this distinction between prediction and estimation. And I want to go one level deeper from a very applied econometric perspective. And so the starting point for me very much in studying machine learning was kind of, I thought of machine intelligence and AI as this kind of amazing futuristic thing where we will like communicate with robots, for example. And then realized that many machine intelligence applications are actually already available. Like we have phones that do something like image recognition, that can do automatic translation, that can do many things that I would have thought are kind of amazing feats of the future when I thought about it a few years back. And so the interesting insight here is that when I first took a machine learning class, like I expected this to be about AI and how we can program a computer and explain to a computer how to be intelligent. And that is very much old school AI, where you kind of explain the computer how to deduce from human intuition and introspection how to solve a problem. For example, whether a certain pixel map is actually a face or is not a face. And what I found very surprising when I first took a machine learning class, that it felt much more like statistics. It didn't feel like that at all. It felt more like you take some training data and you induce a relationship between some X variable, like the pixels in the image case, to some outcome variable, like is this a face or not, from this training data, very much in a way that you would have done in statistics. And so the first question that I had about this whole literature was really like, why isn't this just statistics? What is new here? Because when you take a machine learning class, one of the things on the curriculum will be linear regression. So you think, okay, well, I went all this way to the computer science department to take a fancy machine learning class, and now they're telling me about linear regression. So what's going on here? And so there's, one obvious way in which machine learning is different from the classical statistics, which is that it works with very high dimensional data and it uses very complex functional forms. But I don't think that's all of the story. The question is really, how can this work when we do the same thing that we used to do, but do it with very high dimensional data? And this is what my talk today is going to be about. So the main takeaway I want you guys to take away from this, and also from Sendhil's earlier talk, is really that machine learning doesn't just provide a better answer or a different answer to the same question, but the difference between machine learning and many classical econometric tools is really that the question itself is different. In the sense that the question that machine learning typically asks, and here I'm talking about supervised machine learning, can talk a little bit more about other machine learning methods, is to answer a prediction question about finding a good predictor, so solving a y-hat problem, while many tools that we are very familiar with of the OLS kind in applied econometrics are really about estimation, so finding a parameter value beta hat. And so that allows us to go in two directions. First of all, as Sendhil pointed out, it allows us to tackle new questions where we really need a good predictor, and prediction is key. But second, it also requires a lot of care when we interpret the output of a machine learning exercise in terms of estimation or even in terms of causation. And so what I want to go through here is a very applied econometric take on, first of all, how does machine learning actually achieve that feat of still being able to predict well in high dimensions? Second, based on this very simple understanding of what machine learning does, what goes wrong if we interpret machine learning naively in terms of the output of an estimation exercise? And then third, how does this matter in an application, and what are ways forward? And specifically in the third point, I hope to convince you that there's somewhat of an emerging applied econometric or general econometric approach to bringing together machine learning and estimation tasks. So with that, let me go through this first point, which is about the secret sauce of machine learning. So how does machine learning actually achieve this? I'm going to go over this rather quickly because I know many of you are familiar with machine learning techniques. I've already taken classes in that. So this is more about connecting the dots, but please feel free to pause at any point if I'm going too quick or you have a comment or question. So first of all, the goal of prediction of machine learning is really prediction. And the typical setup for a supervised machine learning problem that I'm just repeating here is that you have some training data that has labels in machine learning speak, which means that you see the y outcome and you see the x covariate, which you would call a regression in the case that y is continuous, or classification when y is discrete. And then you usually also have some loss function. Your goal is going to be to predict y from x for instances where you have the x, but you haven't yet seen the y, in a way that the average loss between the predicted y and the true y is as low as possible. Now, as I said, this looks very, very similar to classic econometrics. One first difference between machine learning and econometrics here is simply that these things are called differently in the econometrics world versus in the machine learning world. So as you may have seen when you've read papers across literatures, y is usually called an outcome variable in econometrics and a label in machine learning, while the x variables are typically called features in machine learning. But very much this looks just like a typical regression setup as we know it. And so let's think about how we would go about solving this in a classical econometric OLS type approach. So our goal is, if we assume that we have a regression problem where our loss here is L2 loss, meaning that we're just interested in minimizing mean squared error, then our goal will be to get small mean squared error out of sample, meaning we want to find a function that predicts the y outcome as well as possible in a sense that it minimizes out of sample mean squared error. And so our typical approach would be that we choose some function space. For this talk, I'm going to focus on linear functions just because they're most familiar to many economists. And then in the training data, rather than solving this problem of finding a parameter that minimizes the true out of sample error, which we can't see because we don't see what will happen in a new sample or an expectation overall, we replace this expectation here by what happens in the sample by its sample analog. And rather than solving for the true expected out of sample mean squared error, we instead solve for the function that minimizes our in-sample fit according to the same criterion, because that's the criterion we have access to. That's the thing we can measure. We can't really see how our function will do on hypothetical points out of sample, but we can see how it does on the data we've already seen. So we're going to choose our function class. We're going to minimize the loss on the data we've already seen. So just going to pause here and say, okay, why is this a good idea? So what do we know about OLS here that tells us that this may be a good idea? And then secondly, is this also the right thing to do for prediction? So just opening up here, these are not meant to be complicated or trick questions. I just wanted, if some of you want to engage here, like just ask you guys, what do we do about OLS here? What do we know about OLS that makes this appealing? And what do we know about it for prediction? Sendhil, what do you know?
Sure, I was going to say, surely somebody will want to dive in and answer Jann's question. What optimality properties does OLS have here? Someone take one for the. I mean, someone's got to break the ice.
Yeah. So I think the basic thing here is just that it's the best linear randomized estimator.
Can you say it again? I had problems understanding you.
Just that it's the best linear unbiased estimator.
Exactly. So it's the best linear unbiased estimator. I mean, that's exactly what I was looking for here. So what does it mean? It's best. That sounds great, right? We like best. But it is best among linear. That's also okay. Let's just stick with linear right now. But it's also only best among unbiased estimators. So if you want an estimator that is unbiased with respect to the coefficient beta, and you are in a case where the error terms have a certain structure, then you know that this estimator will be the one that has the lowest variance, and therefore also the lowest mean squared error actually among all unbiased estimators. But I didn't say anything about that we cared about unbiasedness per se, right? Like we actually want to find an estimator that is good for prediction. And so in this case, the answer whether it's optimal for prediction is generically no, as soon as the data is high dimensional. And there is very classical statistical theory going back to the 50s and 60s that tells us exactly what this means here. In this case, it means that under some assumptions about the error structure, so assume errors are normal, for example, as soon as there are at least 3 covariates or 3 features in machine learning space, which here is kind of our metaphor for being high dimensional, then we know that there is generically estimators that are actually better at predicting. And they do that because they are not unbiased anymore, but they trade off some bias against some variance. So this is usually captured as a classical bias variance trade-off, where I can write the loss that I obtain as a combination of a bias part, a variance part, and an irreducible error, where I can't do better than predicting the component of y that has a signal out of sample. Now, what does bias here mean? Bias means how good I am in predicting beta on average. So on average, do I get to the right beta? Variance here means jaw to jaw, how much variation is there from one beta hat jaw to the other? And so the classical way that this is framed is as a trade-off between bias on the one hand and variance. For machine learning more generally, I like to think of this as an approximation versus overfit trade-off. So overfit means how much does each sample jaw fit to the specific noise term in the specific sample. That creates variance in this linear case with a mean squared error, where we can write things similar easily in those 2 parts, versus approximation. Approximation means how well am I at actually approximating the true underlying function. And so there's a trade-off between those two. The more flexible my functional form is, the more I'm able to approximate the truth well, but at the same time, the more I'm overfitting. So the more I'm also fitting not just to the signal part, but also to the error part. And so that trade-off is one that makes it hard to predict well in high dimensions. And this allows me to improve over simple methods that put all the emphasis on one of those, specifically OLS, putting all the emphasis on minimizing bias, or a very general, very flexible functional form, reducing approximation error, but then producing a lot of overfit. So how would this go? So assume I have my blue points here, which are the sample that I fit on, but I also have some red points, which are out of sample points that I want to predict well on. And remember that our goal of machine learning was to take a training sample and then do as well as we can out of sample in predicting from the training sample to the test sample. Now, if I use the very simple linear regression here, the loss in sample will still be relatively high. I won't be able to fit those very well. And in general, by using this, I can't approximate a complex functional form very well. And if I'm indeed moving to a more complex form, for example, in this case, a quadratic, just for illustration, I'm able to approximate much better what goes in my sample. And in general, I'm able to find a much more well-fitting function if I knew the truth. The same goes on as I add more and more degrees to my polynomial. But at the same time, the more flexible my functional form is, the more I will also fit to the idiosyncrasies of the training data set in a way that does not necessarily help me to predict well out of sample. And indeed, it turns out that in this case, actually, the simple linear function that didn't have any higher order terms was actually better, because the moment that I'm getting more and more flexible, that moment I'm also getting worse out of sample, because I'm starting to fit to the error terms rather than to the truth signal. Okay, so therefore, in general, while I can get better and better at in-sample fit, so blue here is the in-sample fit, at some point, my flexibility means that I'm actually getting worse out of sample, and the additional flexibility that my functional forms that I may want to use offer, and this additional flexibility doesn't help me anymore, but that starts to hurt me. And therefore, if we think of what machine learning needs to work, it's not just that we require very flexible functional forms, but we also have to think about how we can limit the expressiveness of those functional forms to create good predictors. And so when I think of what is kind of the secret sauce going in machine learning, the first two ingredients that we now have on the table is, first, we want very flexible functional forms to be actually able to capture relationships between the y variables and the x variables in ways that our very simple econometric models may not. But second, in order to make them work, we also want to limit expressiveness, which we usually call regularization. So let me just go through the canonical examples. I'm sure many of you know those. So feel free to make any comments or ask questions here if either any of this is not clear or you want to add any points. So rather than running OLS, for example, we could instead run OLS with a constraint where we say we still want to choose among linear regression coefficients. However, we want to reduce the complexity that I have, for example, by using some norm or pseudo norm that bounds the complexity. So a few familiar and popular ways of doing that would be the so-called L2 norm, which is not really a norm, which simply counts the non-zero coefficient and says, instead of fitting a linear regression with all coefficients, I'm going to fit a linear regression where I'm only going to allow to use a set number of coefficients, which here would be called C. So for example, I'm running linear regression on 50 variables, but I'm only allowing 20 of them to be non-zero. Now, it turns out that that problem is non-convex. It's a hard optimization problem. It's not generally feasible to solve this one well. So instead, what is an alternative is to use lasso regression, which replaces that constraint on the number of non-zero coefficients, instead by a constraint of the size of the coefficients, where I'm summing up the size of those coefficients. And this gives me lasso regression if I also write this as a Lagrange. So on the previous slide, I basically had minimize the difference between the realized y and the predicted y, subject to the L1 norm being at most C. Here I'm representing this by a Lagrange optimization problem where I'm solving this constraint problem by putting a shadow cost on deviations from this condition, by basically adding a cost to everything that makes this coefficient larger. So what does lasso do? So lasso now solves a constrained or penalized linear regression problem where I'm still trying to get as close as possible to the truth, but I'm doing so by also adding a cost for very complex functional forms. And the specific structure of this constraint means that the L1 norm, so this is in parameter space beta here, that the L1 norm is bounded. So say the L1 norm, as in this picture here, is bounded by 1. So that means that I'm now searching for coefficients in a larger space subject to that norm. Because of the fact that this constraint here is convex, but is not smooth, and it has those corners on the outside, this will actually make the solution to this likely to be sparse, meaning that there will likely be many coefficients that are exactly set to 0, because it's likely that solutions fall exactly on the corner of this feasible region. And so indeed, in general, we can show that under some generic assumptions that the number of coefficients that can be non-zero here is basically at most a sample size. So if you fit OLS, you run into problems the moment that the number of coefficients is larger than the sample size. I mean, you run into problems even before that with high-dimensional linear regression. But at that point, you can't actually identify your coefficients anymore, or you can't find a unique solution. And that is also the maximum number of non-zero coefficients that the lasso can have. So you can still run the lasso for problems that have more parameters than the sample size, but you will never find more than n non-zero coefficients under some genericity assumptions. Okay, so what does lasso do, therefore? It basically does something very similar to this hypothetical method that I started with, which was running linear regression subject to a constraint on the number of non-zero coefficients. What it does is, by penalizing the coefficients, it also produces sparse solutions. It also shrinks in addition to that, because your lasso will have some cost on the size of the coefficient, but primarily it produces sparse solutions. So a second thing I could do is I could instead use an L2 norm. So I could penalize by putting cost on the sum of squares, which would be equivalent in the picture that we had before of putting constraints that the coefficients fall within balls around the origin. And so unlike the lasso, which produced sparse solution, this solution, and Sendhil calls it socialist, creates solution where the coefficients are likely to be distributed. So rather than picking out a single coefficient that is non-zero, this solution tends to produce coefficients that are more equally distributed, meaning that in doubt, I would produce coefficients on all the variables that are non-zero rather than producing sparse solutions. I should also say that this could be interpreted as a Bayesian posterior, so you could analyze and understand ridge regression as what you would get if you had a linear model with normal data and you calculated a Bayesian posterior, and that would give you exactly the same solution. Okay, so this is just to give some examples of what I think the second main ingredient of many machine learning methods is, which is some sense of regularization, meaning some sense of reducing the complexity of the functional forms you use. For linear regression, the most popular versions of that is the lasso, ridge regression, or some combination of those, which you may have heard of, and is called the elastic net. So that structure of having some function class, of having some regularizer, and then having some optimization algorithm that solves the function class subject to the regularization constraint, that's not just specific to linear regression, but that principle is generically there behind many supervised learners. So one other example are regression trees, where I recursively grow a regression tree that splits at every node one of the features in my data by deciding whether to go left or right based on the value of that data, and thereby being able to represent much more complex relationships that includes interactions between variables in ways that would be very hard to model using linear regression. And so in the case of regression tree, I have the same problem as before. If I, instead of using a very, very complex linear regression that may overfit too much, want to avoid overfitting here, I can now constrain the complexity of those regression trees, for example, by limiting the number of levels that I allow, or by limiting the number of individuals that fall within one of the leaves of my regression tree. So what's the advantage of considering models like trees? Well, if I use something like an OLS regression, it enforces a very linear global structure. So in that way, OLS as a function is very globally constraining, because my OLS regression means that the effect of one of the variables I include is the same no matter the values of the other variables. If, on the other hand, I'm using a regression tree, I can model interactions much better, and I can instead cut the variable space of my features into places that is not globally constrained, but instead produces very local solutions. So I won't have much time to go into detail of those others. I just wanted to point out that, as one other example, the structure of supervised learners is very general. It usually contains some function class, it contains a regularizer and some optimization algorithm that gets us there. And that would also include things like neural networks, where the function class would be complex neural networks. Regularization may, for example, work by constraining the number of layers that my neural network has, by constraining the connections that that neural network has, or by doing something like dropout, or by restricting the amount of optimization that goes into fitting it. So now I have talked at length about the idea that we have to constrain the complexity of functions in order to turn them into good predictors. And I've mentioned some examples that are familiar to most of you. But all of those examples require some choices, and specifically they require the choice of choosing how much complexity to allow. So in the case of ridge or lasso, we would have to choose how much to penalize for the complexity. In the case of the tree, we would have to choose how deep of a tree to grow. In the case of the neural network, we would have to decide how many layers, for example, to include in our neural network. So how would we go about choosing those? And what can we do here, given that this is a prediction problem?
I mean, I think the normal strategy is to try out different options, maybe on a training set, or split your training set and then see how they work out on a holdout set. Yeah, ultimately having a test set that you then finally evaluate everything on. I guess the words might differ by subject.
Exactly. So let me write both words here. So I totally agree with you. So the whole trick here, and this may sound like self-evident to you guys because you may have seen cross-validation and training test splits before, but it's actually, I think, a deeper trick that is very specific to the fact that we're doing prediction. So in the end, we can estimate how well we predict out of sample because we can do the out of sample in sample. So rather than waiting for out of sample and seeing how well our prediction function will do on some hypothetical new data points that we don't have yet, we can simply take our data set, we can randomly split it into a training data set and a test data set. We can fit our function here, and then we can evaluate it on our test set. So why does this help us? Well, it helps us because prediction quality is something we can actually measure. We can actually estimate, we can get an unbiased estimate, and we can confidence intervals for prediction quality. So exactly because we are talking about prediction here, we are able to evaluate how well a prediction algorithm does by simply taking a random split between training data on test data, by fitting our function on the training data, and then evaluating it on the test data. And then we can, for example, do that for different values of the lambda. So let's say we are fitting different functions f at lambda here. We evaluate different functions f at lambda on the right. In this way, we can get unbiased estimates of the performance at different costs we put on the lambda parameter, or different values we choose for the lambda parameter, which here is the cost of complexity. And then we can use the data itself to decide how much complexity to allow. And this is really possible because we care about prediction. We care about something that is inherently observable. And so, for example, what we could do in this simple case here, we could repeat the exercise as before, but we could first cut our data into a test and a train data set. We fit on the train, we test on the red test data set, and then we would immediately see that in this case, the easiest or the best way we should go is the lowest complexity. Now, there's an additional trick here, which is this is very greedy because it destroys a lot of the sample. So in this case, for example, I assume that in addition to my 8 training data points, there were 8 additional data points that I was able to use for doing that. Now, let's take the case where I only have my 8 training data points. I don't have any additional holdout sample. So what I can do in this case is I can repeatedly create holdout samples by doing cross-validation or cross-fitting in general, where I repeatedly leave out some of the data points. I fit only on part of the sample, and then I evaluate on the left-out samples. So assume I only had 8. What I could do is I could repeatedly leave out 2 of the sample points randomly. I could fit only on the respective training data sets. I would then evaluate on the respective test data sets, and then I would average out the performance in order to get a measurement of how well I'm doing. And this is the familiar cross-validation in order to do regularization, where rather than creating a holdout, I go one step further and I do cross-validation where I create repeated holdouts so that I end up using every sample point at some point in order to do evaluation on. For every draw, I get some error, and then I average those errors in order to get the cross-validation error. And then I choose the complexity of my function based on that cross-validation error. So therefore, I would say that the third ingredient in many machine learning approaches is not just to say I use very flexible functional forms and I constrain the complexity, but also leveraging the insight that because this is a prediction problem, third, I can also use the data itself to decide how much complexity to allow, which is usually called tuning, and is often done using cross-validation. Sendhil, did you want to make a point?
Yeah, I just wanted to ask a question for the group. Because you mentioned this in passing, Jann. It's like, oh, you can do this for prediction. If you go back to why you can use the holdout set. Is it obvious to everyone? I mean, can anyone explain why can't you do this for estimation? I mean, you can form a holdout set, you can estimate, you can get an estimator, and you can see how well the estimator does out of sample. Michael, you somehow you're muted even though you're not muted. I think you tried to talk, but you unmuted and then something didn't work out.
I was talking to myself. I was trying to get an answer to myself.
You don't observe the ground truth for the estimation exercise. Even if you have the labels, you don't have the betas out of samples, so you can't check.
Yeah, that's just so, I hope you've heard Leon's point. I mean, it's so important, and just I'll repeat exactly what you said, Leon. With prediction, you can check in a holdout set whether the predictor got it right. As Leon said, with estimators, you don't have beta ground truths. I just want to emphasize this distinction because think of how profound this is. Prediction is empirically grounded because when someone gives you a predictor, you can check whether it's working. Estimation is not verifiable. You're just going to jump out of the plane and trust that the assumptions worked and the parachute will open. There's no way to check that the parachute actually opens. And that's like that I think, Jann, you said this, but I'm just trying to spread this out a little bit. It's exactly, that's what makes prediction kind of, that's why in Jann's point about holdouts, it's not the holdout doing the work, it's prediction plus holdout doing the work. Sorry to interrupt you, Jann. But,
no, thanks. I think this is great. And also thanks for the comment. So I think therefore, when we think later about estimation and other approaches, the question will always be in those examples, how can we actually construct something similar, right? Like even in many estimation tasks, the trick will be to learn what we need to learn from the data to be confident that our estimator is good. And sometimes we can do that because in a randomized control trial, for example, we have some guarantees that allows us to do something similar, but it will not just be looking at prediction error, it will be looking at very specific information we can gather. So don't want to jump the gun here, but I do exactly agree with kind of the importance of that point. The fact that we can turn prediction here almost into an engineering approach is exactly because we can verify how well it does. And we don't need a guarantee about the process, how we got there, if all we care about is prediction quality and we can in the end verify that. And I think that's been why there's been so much progress in making this work in a way that we can be confident that it actually does, because we see it work, right? Like we see how well face detector does because we actually see it in action. And that's a luxury we don't often have when we do empirical research that relies on parameter estimation, where we need other methods to convince ourselves that what we find is reasonable, but we can't directly observe it on held out data. And so therefore, I just want to recap this. It actually goes well into the structure of the machine learning exercise. So there is one challenge if we do what I just said. So assume we choose a lambda in exactly that way. We choose the number of parameters or the number of layers in our neural net. We choose the number of layers in our tree, or the number of leaves in our tree. We are using our sample in order to do that. That means that the estimate of quality we get can actually itself be too optimistic. So assume you did that. You chose for the lasso a lambda parameter that worked best. You don't then want to go away and say, oh, now I know how well my predictor does because I did that for different lambdas. I chose a lambda that minimizes that, and I also have the value for it, which is the minimizer, which is the minimum at that minimizer. But you also want to make sure that you keep some additional samples. So this is where the difference between the trained test splits in cross-validation and the final holdout sample become important. So as long as you stick with the following structure, and many structures in practice, many machine learning applications have that structure in practice, even those inside economics, what you would usually do is, or you would usually see is that you take some sample, some fitting sample or some training sample on which you do cross-validation in order to obtain some prediction function and choose the parameters that go into that prediction function. For example, its complexity, the cost you put on the lasso constraint. Then you rerun your sample, your function in that full training sample at those parameters, and then you do a final estimation of the quality of your prediction on data that you haven't touched at all. And so as long as you stick with this firewall principle of leaving any choices you make to find a function separate from the final evaluation of estimating the quality of that function, as long as you do that, then basically the task of finding a good prediction function, if your goal is really just to get good predictors, is mainly an engineering task where in the end you're going to see how well you do. So you don't really need guarantees about how you got there as long as you get to a good result. You still want to use econometrics in order to get guidance about your choices, in order to do those choices as efficiently as possible. But in the end, if somebody comes to you and says, oh, I have an amazing predictor here, as long as you can verify and hold out data how well it does, you should be confident that you can use it if your goal is just prediction, right? So this is, again, going back to this magic that Sendhil mentioned. As long as this is a pure prediction exercise, we can see how well it does. We don't really need a guarantee how we got there. And that said, of course, once you want to start interpreting it, once you want to start to use it in different ways, you may care about other things than just prediction quality. And this is what I want to focus on next. But before I go there, I just wanted to add a few important points here. So I basically said, okay, machine learning often involves those three steps: choosing a flexible function class, limiting its expressiveness, and learning how much to regularize, so learning how expressive to choose your functions. However, there are, of course, important researcher choices left that are very central to any good empirical application, including which loss function do you actually optimize for? How do you manage the data, making sure that you keep the right out-of-sample experiment so that you can, in the end, run valid tests? Choosing which features to use in your data, so how to pre-transform your data, how to deal, for example, with missingness, and which function class and regularizer to actually choose. So it's not like machine learning does all of this for you, but it's a powerful framework to basically find good predictors among a class of functions that you've chosen. So as I mentioned, and these are some features I'm going to go over only briefly because I really want to get to that point of what do we now do when we think about estimation. This framework applies more broadly, not just to linear functions, but also to many tree and forest-based algorithms. It also allows for the combination of models. So for example, I may not just want to use a linear regression that I improve by, for example, lasso constraint and a tree, but I may want to instead combine many of them. And for example, combine linear-based regression with some tree-based regression in order to combine the strength of both, the first being great when there's a global relationship, the second being great if there's a very local or interactive relationship. And in general, it may not be that surprising that on average, these ensembles do very, very well. But maybe more surprising is that in almost every individual prediction task, an ensemble of multiple methods does best, in the sense that there's usually always some complementarity between different functional forms that make ensemble models very powerful. A few specific examples that you may have heard of ensembles are bagging, where I repeatedly take bootstrap samples from the original data, build models, and then average those models. So the most prominent example of that is the random forest, where I repeatedly take samples of the original data. I construct simple decision trees on those, and then I average the predictions of many decision trees, which turns out to be a super powerful general prediction method that if you compare kind of the typical structure of a linear regression in this two-variable example and that of a tree, you see that the linear regression has a very global structure that is enforced by the simple linear functional form. The tree has a very locally constant structure where it is very good at finding interactions, but also produces areas with constant predictions. While the random forest, even out of the box, is usually very good at a combination of both, at basically creating a function that is smooth enough while also allowing for the modeling of interactions. Booster trees are another class of functions that have been extremely successful empirically, where the idea is that you fit a first simple tree and then you fit a second simple tree on the error you made in the first case, and then recalculate the errors and then fit the third tree on the errors from the first two and so on. So you're basically iteratively fitting trees to the error terms. And that way of improving simple predictors isn't generally known to work very well. There are even some theoretical guarantees. Works particularly well for simple trees, and it's probably these days the go-to method to just get a good out-of-sample predictor on social science type data where maybe a neural net may be too complex. Okay, so why I'm rushing through this so quickly is that I really want to get to the question, what is new here? How does this relate to the existing econometric tools? And spend the next 15 minutes discussing what happens if you want to use those tools, but are you really interested in some kind of estimation, what issues arise, and what playbook arises to bring those two together. So first of all, I just wanted to say, from an econometrics perspective, there's a lot here that has already been known in statistics and econometrics that is basically new names for similar things. Specifically, the idea that we can do better at predicting in high dimensions than using some simple unbiased estimator like OLS goes back to the 50s and 60s, most famously associated with a paper by James and Stein in 1961 that showed that as soon as linear regression has at least 3 covariates, we can do strictly better at predicting if we don't care about unbiasedness. Random forests themselves come out of statistics associated with Leo Breiman. And there is a large area in econometrics that studies non and semi-parametrics, SIF estimation, and Bayesian estimation, which can all be seen as variants of the structure that I just talked about. So, but still, clearly something has happened here that goes beyond these innovations in statistics and econometrics. And so some of the ingredients that I think have come together here is, first of all, the availability of data. That involves very complex data, that involves the ability to access that data in a structured way. For example, for text data, for image data, but also just for very complex social science data. Second, the ability to actually compute those things and to actually fit a neural network, for example, or to even work with very large data sets on either a server or your local machine. And then also just innovations in functional forms we use. So neural networks, for example, have been around for a long time, but only, with this combination of data computation and specific functional forms that actually work for specific tasks have they become as successful as they are these days? So with that said, I now went through kind of those basics here of saying, we have flexible functional forms, we limit their expressiveness, and we learn how much to regularize from the data. So one question is now, assume we do all that and we have a nice prediction function, what do those features imply for the properties of the resulting prediction function? And how can we therefore use that prediction function in applied work where prediction may not necessarily be our main goal? And so I first here want to go over the question, what goes wrong if we interpret machine learning naively? So what can we learn about the world from FF? So often we are interested in some kind of inferences on the relationship of the x variables, of the y variables to the x variables. So for example, we may want to know, how does y change when I change a specific x variable? This may include causal inference questions, where we're specifically interested in the what would happen if question, which is holding everything else constant, if only I changed this one x, what would happen to the outcome? So that would be the rain dance example from Sendhil's talk earlier. So that, of course, is particularly tempting when the output has a common form. For example, I fit a lasso. The lasso conveniently didn't just give me a linear regression set of coefficients, but it also gave me linear regression coefficients that are 0 in many places. So it's very tempting to simply interpret this as, oh, great, now I know which variables are important, and now I know which variables I should choose if I want to affect the outcome in some way. However, I'm now going to ask, to which degree does this come with some of the guarantees we are used to from simple parameter estimation? So to which degree does this come with guarantees of unbiasedness, of consistency, meaning that the estimated coefficient in large samples approximates the true coefficient? To which degree we can do inference? So for example, can we show that these coefficients are asymptotically normal? Can we calculate standard errors? Can we test these coefficients? And to which degree is that inference robust to violations of the assumptions about the relationship of y and x that we may embed in our models? And the context in which I want to study this as an illustration is specifically lasso. I'm going to talk a little bit about, in the end, how general I think those results are. So as a reminder, what the lasso does is it puts penalty on the coefficients in a way that does not only shrink the coefficients, so it doesn't only favor smaller coefficients, it also, in the process, makes many of those coefficients exactly 0. So in that way, it's capitalist. It gives much of the predictive power it associates with a single variable. So it doesn't spread out predictive power between coefficients, but instead selects a few that are non-zero. So what does this concretely mean? Rather than running OLS, which here I'm illustrating in a simple default exercise where my interest is predicting default from some information in a credit file. So why is this an interesting example? This example comes out of studying fairness considerations in using machine learning for underwriting. So basically, banks using machine learning in order to decide who should get credit may resort to those more complex machine learning tools because they are basically facing a simple prediction task of predicting based on a credit file whether somebody is likely to default. Okay, so rather than running OLS on many, many variables, what Lasso does is it runs OLS, but it puts a constraint on it that means that many of those variables will actually be 0. And so, as Sendhil showed before, one way in which we could now test whether the information that we get from that is actually good information about the relationship of default to those variables is we can just empirically test what happens if we do this many times on similar data. So Sendhil talked to you guys through this barcode graph before. This is in a slightly different application. This is in financial data rather than in house prices. And here the focus is on understanding implications for the regulation of those algorithms. But I'm using this here just as another econometric example. So on the x-axis, we again have the iterations that we went through here in taking subsamples of the same data. On the y-axis, we have coefficients on in total of 80 variables. And as you can see, while the lasso that is fit on data from the same DGP multiple times has some persistent structure where some of those variables are chosen every time, many of them look more noisy and are sometimes there and sometimes not there. So there's no strong structure here in many of the other coefficients. So, okay, what does this imply? So that just means that if you thought that this is consistent, if you thought that this converges to the true coefficients and you can learn from those, that should be a warning sign. That should be a warning sign that there's something going on that keeps you from being able to say, oh, I learned from the lasso which variables specifically matter. And so why would that be the case? So what do you guys think, like why in this case would the selection change so much from one draw to the other?
The variables could be highly correlated with each other. So it's picking one or another based on different draws.
Exactly. So Anna, you're exactly spot on here. So it could be that these variables are just very correlated, right? Take the exact extreme case where I could basically learn about somebody's age from a combination of their other variables, which is very plausible. Like people at different ages may have a different financial history. So I may learn a lot about their age from those variables. So that means I can basically write a function that does not include age, but still contains exactly the same predictive information. And from a prediction point of view, that doesn't really matter, right? Like I can easily take one or the other. It basically gives me the same information, assuming that the relationship of age to those others, I can also approximate pretty well by linear regression. And while they will be slightly different, as long as I hold the distribution constant between training and test set, the properties of those two prediction functions will be very similar. And indeed, if all I care about is good prediction, I shouldn't worry too much about that. But if I care about estimation, or for example, I care about understanding whether certain people are treated differently, or how I should change something on the right-hand side in order to affect the left-hand side, then it becomes of primary importance that I'm exactly able to distinguish whether the main driver here is age or whether it's income. But if it's just prediction, I just care about predicting on the same distribution, then I don't really care about that. And so what kind of biases can happen here? So I'm just going to go over this briefly. So assume now I run a lasso, and I have a numerical example here. I have the slides in the Slack channel as well, in case you guys want to follow this in more detail. But all kinds of biases can happen. So assume that two variables are very highly correlated. So in this case, x2 and x3, which are both included in the function, are highly correlated. Then it could be that one of those coefficients is simply set to 0 because it's more efficient for the lasso to only use one of the coefficients to express the relationship on both. And that would be the case if the coefficient, if the price that lasso puts on complexity is relatively high, so that adding a higher coefficient would be inefficient. And the correlation of x2 and x3 is relatively large, so that basically just replacing this function by y equals x2 is approximately giving you a good enough prediction at a far lower cost in terms of the size of coefficient. But it can also be that lasso actually starts to include some variables that are not even in the original function. So assume, for example, this is like, of course, like cooked up a little bit just to make the point. Assume that there is a variable x1 that is not actually in the true relationship between x and y, but that happens to be very correlated with y in a way that is not structurally correct, meaning that it is correlated with y, but is not actually the true functional form. The lasso may prefer to just use a single variable x1 to including both x2 and x3 in order to capture the relationship. And finally, even if a variable that is truly in there is included, it doesn't mean that there aren't also biases. So a first one is that assume in that case where I'm omitting x3 and I'm including x2, even in that case, the coefficient I get on x2 will be heavily biased because I've omitted some correlated variable. So the lasso here, rather than just being prone to biases that OLS would also be prone to, actually actively creates omitted variable bias. Because it actively excludes some variables, there may be some other variables that therefore have a biased coefficient. Now, and then finally, even if x1 and x2 are actually both selected, so even if there is no selection issue here, and exactly the right variables are selected, then the lasso would still bias them towards 0 just because it puts a cost on the coefficients. But I think the main takeaway here is that lasso can be biased in ways that includes variables that are not actually in a true relationship, that excludes variables that are in a true relationship. And even if it does include the right variable, it may still be that it suffers from additional omitted variable bias because the lasso decides to exclude other correlated variables, which are exactly those that lead to omitted variable bias. So in high dimensions, these correlations will be ubiquitous, at least empirically, and therefore we see pictures like that barcode graph here, where basically the chosen variables switch around very wildly. I'm not going to go over in detail of biases in other cases, but I want to go to the takeaway of this part. So when I think of machine learning as a prediction tool, compare it to a simple estimation tool like linear regression that we're used to, then the main takeaway here is that machine learning is really for prediction, where we care about out of sample loss minimization, while the linear regression is typically built to do estimation, where we want to do inference on coefficients. And so in high dimensions, we have kind of very good predictions, even when the coefficients are unstable or biased or inconsistent, simply because we only care about prediction quality. And in many cases, that is not necessarily a problem for prediction quality. Specifically, many functions that look very different can have very similar prediction properties, and it's very hard to distinguish them. And the very features that we discussed make up a successful prediction algorithm make estimation hard. Namely, the fact that we use the data in order to select among a large class of functions makes it very hard to determine the estimation properties and to get valid estimation. And so let me just be clear what I mean by prediction here, because you could say, well, isn't it also a prediction to say, what would happen if I changed something about the relationship? You sometimes could also call this a prediction. But to be clear, what I mean by prediction is that I really mean that it's a good fit of y to y on data from the same distribution rather than some other distribution where I've made some modification. So when I think of achieving good prediction, it really depends on the feature that I'm able to observe how well I'm doing, which means that the distribution stays the same. It stays the same as the distribution I've already seen. On the other hand, of course, you could also say that machine learning does deliver estimation because the prediction function gets close to the true function in a sense of it produces small loss, right? Like it's basically just one norm I could put on the difference between the truth and the prediction function. But what I mean really when I say estimation here is I'm asking whether I can be consistent, whether I can approximate the function well in a norm that cares about distinguishing between the individual parts of the prediction function and not just its prediction quality. So what we really care about in estimation often is something like estimation consistency, meaning the truth converges, the estimate converges to the truth, not just the overall loss converges. So I want to end on a discussion of what assumptions we would actually need to get valid estimation out of machine learning. And I will then on Friday during my talk on using machine learning in experiments, go into a bit more depth in how we can bridge the gap between machine learning and estimation in some applied examples. But for now, I want to kind of finish this discussion on the question, okay, I've now talked at length in this linear regression example, both about how the lasso tends to solve the problem. I've also talked about the issues that arise when you naively interpret the machine learning output in terms of estimation. So what would we actually require if you wanted to bridge that gap? So which kind of assumptions would we need for valid estimation, for consistency of, for example, lasso? So not talking about any technical conditions here, but just like you guys sense, like qualitatively, what do you think we would have to assume about the data in order to be able to obtain that?
Well, the very first thing you would need is a bunch of zeros, right? You need a bunch of variables that have no value at all.
So I totally agree with you. You would need sparsity. Yeah.
Yeah.
Okay, what else? Yeah, what else do you guys think we need? Like, is sparsity already enough?
I mean, I guess you would say something about the correlation, but you could always orthogonalize, right, your regressors. So
yeah, let's probe that a little bit more. So you said we may also need something about the correlation. So let me go through that step by step now. I like those points a lot. So first of all, one thing that we could get, which is even simpler than what you had mentioned, is we could simply assume, rather than there being lots of zeros, just that it's relatively low dimensional. So we could just assume that the data is actually not that complex. And we could just apply the lasso to a usual linear regression problem and ask, do we, at least in this case, recover the true coefficients? So the first example I want to mention is a very classical statistics example by Knight and Fu in 2000, which basically says, if the true model is a linear regression model, and if I fix the number of coefficients and I let n go to infinity, then it turns out that as long as my lambda fulfills a certain sequence assumption, that I'm actually going to recover the true coefficients. So that basically just says, if I actually apply it in low dimensions, then it works. That's not the most interesting econometric result in this case, because we usually want to apply this when the dimensionality is high, which is not well modeled by just holding k fixed and letting n grow. So instead, I'm now going to go to the area that you already mentioned, which is the area where I actually want to be able to model high dimensions. So here are in one of the kind of most important papers in the literature that expresses the assumptions under which we are consistent. Here are the assumptions that they make. So the first one is exactly the one you mentioned. It is sparsity. So sparsity meaning that there is a separation between the variables that are in the model and those that are not in the model, where the variables that are in the model have non-zero coefficients, the variables that are outside the model have zero coefficients. There are a few additional assumptions that I need here. I also need basically that the coefficients in the model are all relatively high, so they don't go to zero fast enough. And the coefficients outside the model are either very small or they are exactly zero. And then I have a third assumption here that says that the x's that are included in the model can't be too collinear. So the x's that are in the model, they can't be too correlated, because otherwise I can't distinguish between different variables in the model. But you also mentioned something that is actually stronger than any of this. And that's actually about correlation that goes beyond the variables in the model. So far, this, I think, sounds relatively reasonable. I could just apply this when I know that my model is very simple, when I know that the model coefficients aren't too small, and when the x variables are not too collinear. And I could also work with transformations here, as you suggest, if that was the case. However, there is an additional very, very strong assumption which also controls the covariance that I have between the variables that are included in the model and those variables that are not included in the model. And specifically, the irrepresentable condition in this paper here says that whenever you regress some of the variables that are not included in the model on the variables that are included in the model, then the regression coefficient has to be very small. So in other words, the correlation between the included and the excluded model has to be very small in order for you to actually be able to correctly assign which part is belonging to the model, which part is not belonging to the model. And my take on that, it's a very strong assumption. It's not one that we can easily break by reparametrization. And it is one that is thought to be close to necessary. So there's probably a little way around that. And then finally, I want to mention here as another negative result that it's also generically hard to do any inference after selection. So using the data to select and then doing inference on it is also very hard. So now I'm already over time here. So let me wrap up and go through what I think the main takeaways for applied work of this analysis, of this very brief applied analysis of kind of y hat versus beta hat is. So machine learning provides quality predictions, but the prediction quality, while it comes with guarantees from the holdout, it does not typically come with estimation consistency or guarantees about the interpretation of the coefficient of that model. Hence, by itself, we don't get structural interpretation or counterfactual extrapolation like causal inference out of a machine learning model. And as a side note, it's also very hard to do inference, like things like the bootstrap typically don't work in those cases. And in my eyes, that's not just an issue of implementation. It's not just that we're using the wrong method to do inference in high dimensions. It's inherently a limitation that consistent estimation is inherently challenging if you're considering many, many variables and many, many possible functions, while for predictions, that's okay, because many of them are basically the same to you. So, and at the core of that is that prediction quality can be observed, estimation quality cannot, and therefore it will be much harder to do high dimensional inference on coefficients than it will be to still get good predictors. So I go on Friday over some examples of how we can bridge that gap. And I think there's an emerging econometric playbook here that bridges that gap by basically distinguishing between the prediction part on one side from the estimation part of another. One example is, for example, an IV estimation, where I could see the first stage as a prediction part, the second part stage as an estimation part. And I saw that one of you posted a link to some recent work by Greg Lewis in chat, which I also like a lot. And it combines those two by using smart sample splitting that guarantees certain estimation qualities, while also leveraging high prediction quality. And so let me then wrap up with something that I started this small lecture with, which is that when I think of machine learning and its relationship to standard econometrics, I don't just want to think of this as offering a different answer to the same question, but instead I want to think of this as providing an answer to a different question, where machine learning answers a prediction question, while many tools we are very used to in applied econometrics answer an estimation or beta hat question. And therefore, I think there are some exciting opportunities going forward for research that we hope to cover this week. First of all, applied research opportunities where we can use new data, we can tackle new questions or using improved methods, and we can be more systematic about data-driven choices by adapting methods or paradigms for machine learning. Second, there are also very exciting econometric questions that kind of bridge the gap between y hat and beta hat. So basically, how can we use good predictors if we actually have a parameter estimation problem by effectively using the machine learning part for some nuisance components? And as well as actually in econometrics, something I'm very excited about recently is also going beyond the simple supervised learning. So going beyond the simple prediction. Machine learning also offers tools that work very similarly on, for example, clustering or on dynamic experimentation. And so things like unsupervised learning and bandits are also things that will appear in our program this week. And then finally, I think there are also important opportunities in policy and theory that ask the question, what happens if market participants or if like individuals, agents in our models interact with the use of machine learning? Like questions, for example, about transparency and fairness of machine learning that I really inherently think require input from economists, because they are inherently about strategic interactions of agents and about welfare consequences, and therefore I think require all of our input. So with that, I'm gonna end here. I think we will take a 10-minute break and then return for a social. I'm just gonna stick around here and get some food, and then I'll see all of you again.
Thanks, Jann. Yeah, I think it was scheduled for a 15-minute break, so let's maybe reconvene at in 15 minutes. And for those listening on the public stream, the next public talk is going to be at 2 p.m. Central on the YouTube channel.